Okay. So here's what we have left before Christmas. We got momentum, which is the next unit, which is both linear and angular momentum. And that's going to take us 9 days to get through. So that means the last, or the test, we'll have the test over momentum a week from this Friday. Okay? And after that, we've got like work, energy, thermodynamics, gas laws, buoyancy, just kind of a hodgepodge of stuff. And then we'll finish all that up before Christmas, okay? And then at Christmas, you're gonna have like a 2-day lab final and a comprehensive written final, okay? So if you really want to plan ahead, that's what we're gonna be looking at. And if we can get to $1,000, that'll all happen those last 3 days with your t-shirt having red and green hair.
So too busy working to even.
We still got a ways to go on that, but we're over 20% there. Okay. All right, so let's talk about momentum. So momentum is one of those deals that you kind of intuitively understand, and you use the word a lot. And if you've ever watched or played sports or watched sporting events, you can feel momentum shift, okay? It might be a base hit in baseball. It might be a three-pointer in basketball. It might be a goal in hockey or in soccer, okay? But you can physically sometimes feel that momentum shift. So sportscasters will take advantage of that. They'll go, oh, you know, Team Coyote has the momentum, okay? I guarantee you that guy's never studied physics, but he likes the word. So momentum of it in and of itself is a fairly simple concept, and it's one of the simplest formulas you'll ever see. So momentum is this. It's just mass times velocity. Okay, that's it. That's the formula for momentum. It is absolutely one of the easiest formulas you will ever see. Now, the reason that even though we talk about momentum, we use the letter P because M equals mv would just look weird. Okay? And the letter P actually comes from the Latin word impetus. Because what they used to think when you would throw something or you would move something, you would give it a certain amount of impetus. And when that impetus ran out, it would stop. So it was kind of viewed as like a fuel gauge. So if I take this rubber stopper and I give it just a little bit of impetus, it's only going to go a little bit and then it's going to run out and then it's going to stop. If I give it more impetus, it's going to travel further and then it's going to stop.
Well, yeah, that makes
And they
sense.
even had that idea with projectile motion. Like when you were like trying to hurl like a big stone at a castle, so in their mind it would literally go up until it ran out of impetus and then boom, it would just fall straight down. Okay, it's like, okay, we're done, boom, okay? Had no idea of parabolics, it would just go boom, stop, okay? So that's where the letter P comes from, okay? And beyond, it would just get confusing if you used the letter M anyway. So, the calculation itself is as simple as it can possibly be. So let's say that I happen to have, and I do, a 1 kilogram mass, okay? So I have a 1 kilogram mass, and let's say I'm moving it at 4 meters per second. Here's as simple as the calculation can get. Oh, okay. I've got a 1 kilogram mass moving at 4 meters per second. So mathematically, oddly enough, I get an answer of 4. Now, there's 2 ways you can write the units. I don't care how you do this. This is purely up to you. So one option is that you look at this and go, oh, that's kilograms meters per second. So if you want to go with that, kilograms meters per second, that's cool. Okay, there you go. It's old school, mass times velocity, just like F equals ma, you can write kilograms meters per second squared. Momentum is mass times velocity, so you could just put kilograms meters per second. If you like that, you're old school, great, it's cool. Now, your other option, which shortens it a little bit, and later on you'll see where this comes from, but you could also write it as Newton seconds. Now, here's why this works. Because kilograms meters per second squared, which is what Newton's is, and if you multiply that by seconds, one of the seconds is going to cancel out. You get kilograms meters per second, which is the same thing. Okay? So I don't care how you choose to do this. You can put Newton seconds, you can put kilograms meters per second. I don't care. All right. That's as simple as momentum calculations get. Okay? Now, do you think momentum is a vector quantity or a scalar quantity?
Vector.
Why?
Because it says so on the sheet.
Okay, but beyond that.
Hey, cute.
Because you're having a velocity.
Yes. And could the velocity be negative?
Yes.
Yes. So if I'm moving this way at a positive 4 meters per second, if I move back this way, I'm going to be moving at a negative 4 meters per second. So I could also have a 1 kilogram mass moving at a negative 4 meters per second, which would get me negative 4 Newton seconds. So in situation number 1, I could draw it as a momentum vector pointing in this direction. The other one, which would be positive 4 Newton seconds, the other one I could have a momentum vector pointing in the opposite direction. Okay? So momentum is very much a vector quantity. Now, if you look at driving your car from the perspective of momentum, okay? It's a simple idea, but to have momentum, you have to have two things. You have to have mass, and it has to be moving, right? So, from a momentum perspective, what's the function of your gas pedal? To make the momentum vector get bigger, right? What's the function of the brake pedal? Make the momentum vector get smaller. What's the direction of the steering wheel? Or what's the function of the steering wheel? To change the direction, right? So, from a momentum standpoint, you have three ways to change your momentum vectors. You can make your momentum vectors get bigger, you can make your momentum vectors get smaller, you can make the momentum vectors change the direction. Okay. Now, so here's a 1 kilogram mass. Patrick, is it possible for this 1 kilogram mass and this plastic penguin, now listen to me very carefully, is it possible for this 1 kilogram mass and this penguin to ever have the same inertia?
No,
Why not?
because their masses are different.
Okay? And the only thing that determines inertia is
The mass.
mass. So no matter where I am, if I'm on the moon, here, Jupiter, it doesn't make any difference. This 1 kilogram mass is always going to be harder to start and stop, okay, because it has a lot more stuff in it. The penguin, it's plastic, okay, and hollow, okay. Not only is it plastic, it's hollow, okay. So this doesn't have much inertia, so it's really easy to get it to start and stop. This solid brass has a lot more stuff in it, okay. It's harder to get it to start and stop. Okay, cool. Would it be possible, Morgan Scott, for this penguin and this 1 kilogram mass to ever have the same momentum?
Yes.
Yes, you're right. Why are you right?
Because they can have the same weight. They can have the same velocity.
Nope. And they could, but then they wouldn't have the same momentum. I want them to have the same momentum, right? So think this through, Morgan. What two things do you multiply together to get momentum?
Velocity and mass.
Mass, right? So this has a really small mass, right? This is a really big mass. So how could I make them have the same momentum? What would I have to do with the penguin?
Make it heavier.
No. Well, I could, but then, no. You're making this difficult. Mass times velocity equals momentum, right? So if this has a small mass, I'd have to make it move faster or slower than this.
Oh yeah. It has to be
Which,
faster.
yes, which one?
Faster.
Faster, right? Faster or slower? Oh, yes. Okay.
Oh yeah.
Don't wait.
Faster or slower.
There you go. Okay.
Got it.
So, because momentum is a product of two things, so I can have the penguin with a small mass moving very quickly, or I could have the 1 kilogram mass with a large mass moving slowly, okay? So it's possible for two objects of unequal mass to have the same momentum, okay? But it is impossible to have two objects with unequal mass have the same inertia, okay? So keep that in mind, okay? Keep that in mind. Now, obviously, the test week from Friday, I'm not going to have 5 pages of questions going, oh, here's a 5 kilogram mass moving at 2 meters per second. Calculate the
not?
momentum.
Why
Okay?
not?
I
Or the
think we
momentum
should.
is 20 newtons per second.
I think
or
that'd
20
be funny.
newton seconds. And the mass is 2 kilograms. Calculate the velocity. Okay? No. So here's the $1 million question, though, Carter.
Yes.
Is it possible to change the momentum of an object?
Yes.
How so?
Changes velocity.
Oh, it changes velocity, okay? Now, later on, you can see that you can change momentum by changing the mass, like a rocket, okay, where it expels fuel, okay? But for now, unless it's a rocket problem, we're going to assume that the mass is going to remain constant. To change the momentum, then, we're going to change the velocity. Now, this is where this turns into a logic problem, okay? So, Cassidy, if I want to change the momentum of the penguin, what do I have to do?
Change the velocity.
How am I going to change the velocity?
You could like increase it or decrease it or change direction.
Okay, increase or decrease, what is it?
The force or the velocity.
Which one?
Speed. Velocity?
But to change the velocity, what do I have to exert?
Force.
Oh, I have to exert a force. Okay. So, what you're going to see is that a whole bunch of things that we've studied, we're going to revisit. Okay? We're going to repackage them in slightly different ideas. Okay? So, let's start with a velocity time graph.
Boy, oh boy.
Okay? Like we're going old school velocity time graphs. Okay?
No.
No.
Back in your wheelhouse?
Yes.
Okay.
I can actually do something.
Okay. So let's say I've got the penguin, and I'm going to push the penguin along at a constant velocity. So what would that look like on my velocity time graph?
A line
Doing what?
going horizontal.
Or a line. That kind of- okay, but you said it with such feeling. A line. Just not a line. A line.
Very confident.
Okay?
It's a
You know,
Yes. Kind of that dramatic. Okay. So we have a horizontal line. Okay? So here's the deal. So does the object have momentum?
that's
Yes. How do you know?
velocity.
It has a velocity, so it has momentum. Right? Okay? So if that's 5 meters per second, and the penguin has a mass of 0.1 kilograms, I can multiply those together. I can go, oh, 5 meters per second times 0.1 kilograms, I get 0.5 newton seconds, right? Cool with that? Cool. All right. So the slope of a velocity time graph gives you what?
Sorry.
Acceleration. So if I'm pushing the penguin along, okay, at a constant velocity, but then I stop pushing the penguin, okay? I stop pushing the penguin. He's not going to do the standing up. He's going to face plant. So if I stop pushing the penguin, what's that velocity time graph going to do?
Slow down.
Slope downward towards zero, right?
Yeah.
Okay, now here's an interesting idea. There's a horrible line. So we do this, right? So the line is sloping towards zero. So Smiling Sam, it's approaching zero. Am I speeding up or slowing down? Slowing down. So I'm going from 5 meters per second to zero. So is my momentum changing then because my velocity is changing?
Yes.
Yes. So here's the deal. If you want to change momentum, this is what Cassidy's saying. If you want to change momentum, you have to change the velocity. If you're going to change the velocity, you have to accelerate. But to make something accelerate, you have to have
Force.
a force. Now, a net force or just a force?
Net.
Oh, it's a net force. Ooh, that's huge, right? It's a net force. So here's the deal. So if I were to look at this graph, and I'm slowing down to 0, the slope of this line represents my acceleration, right? So, is my acceleration going to be a positive or negative number, Michael?
Acceleration's gonna be negative.
Acceleration is going to be a negative number, right? Because I have positive velocity and I am slowing down. True? I'm going to have negative acceleration. So here's what's going to be important. If the slope of your velocity time graph changes, guess what? You're accelerating. If you're accelerating, your velocity is changing, so therefore your momentum is changing. Okay? So to change momentum, you change velocity. To change velocity, you accelerate. To have an acceleration, you have to have an imbalanced force. Right? So it kind of forms this one big circle of logic. Okay? Now, here's a new graph that we haven't talked about. So we said when that penguin was moving at a constant velocity, it had a momentum of 0.5 Newton seconds. So here's a new graph. But it's the same kind of idea. We're going to draw a momentum time graph. Okay? A momentum time graph. Oh, it's going to get worse. So, if I'm pushing Polly the penguin at a constant velocity, what's my momentum time graph going to look like? No, you got to say it with feeling. That was still bad. What's it going to look like?
A line.
Oh, see that? Oh, even that was kind of weird. Okay. Is it going to be a horizontal line? Yes.
Oh.
Oh. Whoa. 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 And that's going to be at 0.5 Newton seconds. Okay? Whoa. Okay, somebody says the word dude, I'm going to flip out. So, don't do it. Don't do it. I won't have to flip out. I'll do it. Don't make me. So, if you have a horizontal line on a momentum time graph, okay, what does that indicate about your momentum? It's the momentum isn't changing, right? You have a constant momentum, right? So you have a constant momentum, which means that you have a constant velocity, right? So what's your net force? Net force is going to equal 0. Okay? Now, notice I didn't say force. I said net force. Because I'm pushing this penguin along, why do I have to keep exerting a force?
Friction.
Yeah, because this isn't the magic frictionless penguin. Okay? Now, if we were on like an iceberg off of Antarctica, and it was a frictionless surface, I could give Polly the penguin a push, and he would probably maintain a pretty constant velocity, right? So, when you have a horizontal line on a momentum time graph, one of two things is happening. Either all the forces add up to equal to 0, or there's just no imbalanced force, and inertia will keep it moving, right? Now, I stop pushing Polly the penguin. What's my momentum time graph going to do?
Slope down.
Slope downward. Oh, because once Polly the penguin stops moving, what's Polly the penguin's momentum?
Not
0. Okay? So, this line's going to slope down like this.
Yo, why they look the
Okay.
same?
Now, let's say that that was 0.5 Newton seconds, and let's say that was at 5 seconds. And then let's say this goes to 0 Newton seconds, and I don't know, 1 second. Let's make it easy. So that would be like at 6 seconds. So here's the question. I'm going from 0.5 at 5 seconds to 0 Newton seconds at 6 seconds. Mr. Cole, can I find the slope of that line?
Yes.
What would the slope of that line be?
See. Yeah, 0.5 over 1, so it would be, or negative 0.5.
No. So, we'd have 0 minus 0.5 Newton seconds divided by 1 second So what units do you get?
Newton.
Oh, how cool is that?
At your photos.
Required force to halt momentum.
How cool is that? So what does the slope of a momentum time graph give you?
Force.
Force. Oh, that's kind of cool,
Cool.
right? That's kind of cool.
Isn't that cool, Kyle?
So,
Oh, rubbing out.
if you have a horizontal line on a momentum time graph, the sum of the forces is going to equal 0, right? Okay, horizontal line. All the forces added equal 0. If this line is a sloping line, that means your net force does not equal 0, and your momentum is increasing or your momentum is decreasing, right? Okay?
Momentum change.
Now, here's the next big equation. It's okay. Force times time equals change in momentum. Now, here's what's going to be important about this. That's going to be net force times time equals change in momentum. Now, here's where the units work out. What units is that net force going to be measured in?
Newtons.
Newtons. What's time going to be measured in?
Second.
Oh, that's why I said you could also express momentum in terms of Newton seconds, because it's force times time.
Smart.
Now, this equation, believe it or not, you all have probably understood since you were probably 2 or 3 years old. Okay? You all have known about this equation. You're going, oh, I do not. Yes, you do. Okay. So first off, I've got a couple of eggs up here. One of them's hard boiled, one of them is raw. So how can you tell the difference?
You crack them.
Spin them. I can crack them, but I really don't want to do, right?
The wall.
So I'll take this one, I'll give that a spin. And notice it spins really, really quickly, right? And if I stop it, hold on, if I stop it, it doesn't spin. Okay, it just stays there. Now, this one's the raw egg. So if I spin it, it spins slower, but if I stop it, it continues to spin. Okay? Because the yolk inside, oddly enough, continues to have momentum. Okay? Whereas this is a solid object. So if you don't know, so here's a life skill as you all go into college. Okay?
Spin eggs.
Spin eggs, right? And here's your other mantra. If you're looking in your refrigerator, and here's just a word of advice like, ooh, is it past the expiration date or not? Just a word of advice. When in doubt, throw it out. Okay? Just as one who's been in a third world country and had food poisoning, I'm just telling you. When in doubt, throw it out. Okay.
Spinner.
So here's how you can tell the difference. Spin it, it goes slow, but if you stop it, it continues to spin. Hard-boiled egg spins, you spin it spins much faster. You stop it, it stops. So that's how you can always tell the difference between the two. So here's what I'm going to do. The wall, come up here.
Magic egg spinner.
Good luck.
I'm going to throw the raw egg, okay, the raw egg to the wall, okay? And I want you to catch it, and I don't want you to break it,
I'm glad I'm not the one.
okay? Got this concept. You ready? Sure.
Sure.
Don't
Okay.
squeeze it with your hands either.
All right, you ready?
Ready.
Okay, now, what did you do when you caught the egg?
Fine. Brought my arms back.
So what were you doing by bringing your arms back? As opposed to just putting your hand up and acting like the wall and catching it.
Increase.
But in both cases, you were slowing it down. If you had your hand like that, you're going to slow the egg down. If you cradle it, you're going to slow the egg down. But what's the difference?
Slow it down slowly.
Oh, slow it down slowly. Okay, now it throws the egg. So what happens is that when people instinctively catch an egg or something fragile, they do this. Well done. Thank you.
Just
All
catch
right, now we're gonna crack.
Now, here's the deal.
You open it.
Here was yonder egg, right? Now, when I threw the egg to the wall, did I change the momentum of the egg?
No. Yeah.
When you first.
When you
Yeah,
throw
because what
it.
was the initial momentum of the egg?
None.
0.
And then you throw it.
I threw it to the wall, I gave it some momentum, right?
Then you stop.
Because if I don't, the egg's not going to go very far. It's like,
Fall down.
move. Okay? If I don't give it force over a certain amount of time, we're not going to change the momentum. So On a momentum time graph, look what happens. So what was the initial momentum of the egg when I threw it?
0.
0. It had no momentum. So I imparted a certain amount of momentum on the egg. Now, a change in momentum is also known as the word impulse. Okay? So impulse and change in momentum mean the same thing. Okay? So if you see the word impulse, that means the same thing as change in momentum. So I gave a certain impulse to the egg, right? So this is when I was throwing it. Now, what does the slope of a momentum time graph give you? Force, right? Gives you force. So this is when it left my hand. Then it was flying through the air. Okay? So our momentum was constant because it was just flying through the air, right? Now, the wall caught it. As soon as it came in contact with his hand, what did you do? You cradled it, right? So what were you trying to do the momentum? Increase the momentum or decrease the momentum? He was trying to decrease the momentum. Right. So he was trying to make that momentum go to 0. Now, think about this. This is where you look at your options. He was trying to slow, and listen to me very carefully what I'm about to say. What Wall was trying to do was decrease the rate of change in the momentum, okay? Which is reflective of this force, which is reflective of the steepness of this line. So what he did, and remember, the slope of a momentum time graph gives you force. He wanted to minimize the amount of force that acted on the egg. Okay, that's what he was trying to do. He was trying to minimize the amount of force. So by stretching that time out, okay, by stretching that time out, he was able to slow the rate of change in the momentum. Now, let's just say he put his hand up like this and he just caught the egg. Would the final momentum of the egg still be 0?
Yes.
Yeah.
But what would happen to the amount of time?
It would drastically decrease.
Drastically decrease. This line would become much steeper. But what does the slope of a momentum time graph give you?
Force.
Force. So if you have a steeper line, guess what? You're going to have more.
Force.
With more force, you have a bigger acceleration. What's going to happen to the egg?
It might explode.
Egg go boom. Okay. So, later we're going to have to give that a little bit of spin back here. So, I need you, gentlemen, the assistants. I need you to hold that.
Oh, like all the way back there. Who's this
So,
for?
I need you guys to hold
This for Sandra.
this blanket up
Josh.
like
Feeling stinky.
okay on the corner.
I called it an
Yeah. Okay, you got this?
Well, you better win.
Okay, got that? Yay,
Like, what's happening over here?
okay? So, now,
Perfect.
No.
hold on to the bottom, and I want you to kind of like tilt that bottom up a little bit. Okay, so I'm going to throw the egg into the sheet, okay? Now, what's the initial momentum of the egg?
More.
0, right? So I'm going to throw the egg, I'm going to give it a sort of impulse, right? What's the function of the blanket?
To stop the impulse negatively.
Yes, to take the momentum back to 0, right? Okay, so initially I'm not going to throw it very hard, okay? Now, if this goes south, it's because you guys let go of the corners, okay? So don't let go of the corners.
Like that.
What did you do?
Specifically
What did I say? Don't let go of the corners. What did you do? You let go
I
of the
wouldn't
corners.
do that.
Okay, are you ready?
This is why I'm
Okay. So, here we go. Right?
Oh, I think it's gonna
Okay? Right?
throw harder.
So, who imparted the larger impulse on the egg? Me or the blanket, or was it the same?
The
same.
same.
It's the same. Why?
Because it's a ratio of speed and force. Time and force.
You're
Time
making
and
this
force.
horribly difficult. Okay? When I let go of the egg, let's say it was going at 5 meters per second. Okay? when it hit the blanket, it went from 5 meters per second to zero.
Oh, okay.
Okay? So the impulse on both of us is going to be the same, right? Now I'm going to throw it a little bit harder. Okay, you ready?
Force, 1 second, or 2 force is
Right.
5 seconds.
So I imported a bigger impulse, but that required more force, right?
Yes.
Okay? More force, more impulse, here we go. Now, I'm gonna throw this one as hard as I can. Okay, you ready?
Throw that card
Now, give us a little bit of big
Yeah,
hard.
right through it.
Lift up the top a little bit. Okay, you ready? Sure?
It cracked in his hand.
That one came apart in my hand.
Oh,
Okay.
no! Child casualties.
That was disgusting. Okay, anyway, so. I know, that actually came apart in my hand. Okay, all right, so, we'll just do it that way. Okay. That was fairly disgusting. We'll just make that go. Okay,
That is literally me when the problem comes up.
that was just gross.
Put it into the science room.
Now, one time I did this, and I had a kid throw it, that's why I don't trust kids to throw it anymore. So we were doing it towards that wall, and the kid, I said, "You're not gonna miss, all right?" No, I play baseball. Kiss of death, okay? So the kid wound up and he threw it, and he went low, and it hit the floor and the bottom of the door at the same time, and that thing completely exploded. I mean, this thing was like a crime scene. There was egg from that door all the way to the lab tables. I mean, it was like an asteroid impact. I mean, it just went everywhere. So at least that one, when it broke my hand, at least it still stayed together. So,
Try it again.
See, the physics of that is smaller.
Just ugly for that.
yeah, I have to take that home and wash that one. Okay.
Can I take the egg home?
Which one, the hard-boiled one? Okay. So, let's look at the situation, right? So here is a completely jacked up graph. Okay. So there's momentum time graph. So I threw it, right? Went through the air, hit the blanket, boom, stopped. So if, let's just say, and I did see this happen once. This was at it was like a hotel, and it was like a science convention. And they were trying to do this demo, and the person threw it, and they overshot it, and it hit the wall behind them. And the wall, it's like for the rest of the session, you see this egg like oozing down the wall. So let's say I didn't, but let's just say that I missed the blanket and I hit the wall. Okay, what would this graph do?
Look the same, but steeper.
Yeah, this would become
The end would be
It'll
steeper.
go straight down.
much steeper, right? Cool with that.
It would not go straight down.
Now,
'Cause there's still time.
but this also goes down to a logic situation. Patrick, where was that tennis ball that you had? Okay, so throw the tennis ball. All right. So I'm going to throw this tennis ball to Patrick, right? Okay. I'm going to import an impulse, right? You're going to catch it. Whoa. Now, throw that back. Now, oh God. Okay. Actually, aim for my hand. Okay. All right. Now, if I don't catch the ball, okay? If I don't catch the ball, if I don't impart a force on the ball, does the momentum change? No, because Newton's first law of motion that says for lack of a force, guess what? You don't change the velocity. If you don't change the velocity, guess what? You don't change the momentum. Okay. Now, two situations. I'm going to catch, let's say Patrick threw me the ball, and I could catch the ball like this, or I could catch the ball like this, right? Exact same change in momentum. Now here's another graph that we're going to look at. And that's a force, and this is going to be important, a net force versus time graph, okay? So, let's look at this. Situation number one, I'm going to catch the ball, and I'm going to cradle it, right? So when you cradle it, what are you increasing? Time or force? Time. To decrease, force, right? So when I cradle it, I'm going to exert a certain amount of force over a certain amount of time, right? Let's just make up a number. Let's say that that's 1 Newton, and let's say that's 2 seconds, right? So if I multiply newtons by seconds, I get 2 Newton seconds. Oh! What's measured in Newton seconds?
Momentum.
Not momentum,
Oh,
change in momentum.
change.
Okay, and there's a big difference between momentum and change in momentum, right? Because if I miss my hand, right, there's no force, there's no change in momentum. So if you have a force time graph, guess what? That area represents change in momentum. Okay? Now, so situation number 1, I cradled the ball like this. I have a small force acting over a large period of time. Situation number 2, I catch the ball just like this. What's going to happen to the time? It's going to become smaller, but what's going to happen to the force?
Increase.
Ooh. Or I could have a situation like this, where I have a big force acting over a small period of time. So in both situations, the change in momentum is going to be the same. So, anybody here ever done gymnastics?
No.
Okay.
Okay.
How do they teach you to land? With your knees locked or your knees bent? Bent. Why don't you want to land with your knees locked?
That's bad.
That's going to be bad, right? It's going to
To your
hurt.
knees.
So here's the deal. When you do gymnastics, guess what? You live and die by this equation. Change in momentum is force times time. So when you land with your knees bent, what are you doing with the time? Making
Increasing
it
bigger.
bigger. What's going to happen to the force then?
Decreasing
It's going to
it.
decrease. You land with your knees locked, time is going to be small, force is going to be
Great.
big, and you're going to break your knees.
Yeah.
Okay? Now, if you become an engineer and you go to work for the safety department of an automobile company, every day you wake up, if you're a safety engineer, and you live and die by this equation, what's the function of airbags?
Stop it fast.
Not stop it fast.
Whoa,
No, to
slowly.
slow you down.
Airbags function to increase the time
So you
to
slow down the force.
decrease the force, right? Because here was the problem. Even up until like the 1960s, safety belts were an option, okay? They were an add-on that you had to pay extra for to get safety belts, okay? And people would go, I don't need safety belts, I'm
I'm cool like that.
a manly man, I don't need safety belts. Here's the problem, you're on a head-on
They
collision,
die.
okay? What are you gonna do when you're on that head-on collision? What's your body gonna
I'll
do?
do it.
Inertia.
Your body's gonna maintain a constant velocity until
You hit the other car.
an outside force acts on it, right? And if you're a driver, what's going to provide that outside force?
windshield.
The windshield or the steering wheel, right?
The heat.
Guess what? That's going to stop you really, really quickly. Guess what? That's going to provide a lot of force. Guess what? That's going to create a lot of pain.
Trauma.
Okay? So the function of seat belts is this equation right here. Seat belts serve to increase the time, to decrease the force. Now, they don't decrease the change in the momentum. Okay? If you're going 60 miles per hour and you're in a crash, your velocity is going to go to 0. So it's not going to alter the change in the momentum, but it's going to change the rate of change in the momentum. So safety belts and all safety features in cars don't try to decrease the change in momentum, they decrease the rate of change in the momentum. Now, this is where this all goes full circle. Okay? Get ready. Okay? Get ready for this action. Okay? Not yet, but we'll get there. Okay. Now, change in momentum is force times time, right? Now, there's a couple of ways that you can write change in momentum. You could write P minus P naught, final momentum minus initial momentum. Just like delta V is V minus V naught, final minus initial. Okay, that's one way you can do this. Now, change in momentum could also be written, change in momentum, as mass times velocity minus mass times v naught. Okay? If you wanted to write it that way in terms of momentum itself. Now, if you wanted to get fancy, what could you do with your mv and your mv naught?
Take it out.
Factor out an m, and you would have m times, right? Cool with this, right? Now, so here's what you're going to see. More and more, we're going to begin to set things equal to each other. And the more things that you have set equal to each other, you have to focus on what's staying constant and what is changing, okay? Are you going to keep the change in momentum the same and look at the relationship between force and time? Are you going to keep the force same and manipulate what happens to the time in terms of your change in momentum? Are you going to keep the time the same and manipulate the force in terms of your change in momentum? So when you're comparing, you have to focus on what you're holding constant and what you're changing. Now, we just said that mass times change in velocity, you could also write this as m delta v, right? It's the simplest way to do it. So m delta v equals force times time, right? Which is change in momentum. But if we divide both sides by time, well, what's the simplest way to express delta v over time? What's your rate of change in velocity, otherwise known as? So guess what? If you multiply mass times acceleration, you get force. So all this is F equals ma repackaged into a rate of change in velocity. Okay? It all is just back to F equals ma. Now, let's say that you're in your car and you want to create a big change in momentum. Okay? Would you hold your gas pedal down for a long period of time and press it all the way to the floor? So you got your gas pedal all the way to the floor. You want to create a big change in momentum. Would you hold it there for a long amount of time or a short amount of time?
Long.
Long. Why?
Because that's how you ramp up your acceleration or
Okay.
velocity using acceleration.
Well, look at it this way. Look at a force time graph, right? The area of a net force time graph gives you what? Change in momentum. So if you want a big area, guess what? You want a big net force acting over a. I want a big change in momentum.
Oh.
I want a big area. So what do I want to have happen?
Big force, big time.
Big force over a long period of time, right? You play soccer. Ball is rolling towards you. You just want to stop it, right? Ball's going to come in, boom, you just stop it, boom, there you go. Now, if you want to take that same ball and project it in the opposite direction, what are you going to do?
Just absolutely kick it.
Absolutely kick it, as opposed to just kick it, right? Okay? Now, think this through, okay? Think this through. By the way, y'all been sitting for long enough. Stop that camera for a second. Stand up, take a stretch. Okay, so here's what I want you to see. You have to focus on what you're keeping constant and what you're changing. So if you want to create a big change in momentum, you want to have a big force acting over a long period of time, right? Press down on your gas pedal and you hold it there for a long time. That's going to create the biggest possible change in momentum. But if you want the change in momentum to remain constant, then that goes down to a situation of a manipulation of force and time. So if your change in momentum is constant, then you could either have a big force acting over a small period of time, or you could have a small force acting over a large period of time. Okay? But that's why I said you have to focus on what you're holding constant and what you're changing. Okay? That's the huge difference. All right. Now, a lot of times when an object is coming in, so Patrick, throw me this ball again. Okay, you ready? So, throw it. So, situation number one, I just catch it. So in this situation, the velocity is going to go from some positive velocity to 0. Now, throw that again. You ready?
Yeah.
Okay. Now, situation number two, I hit it and going in the opposite direction. So situation number one, I just stop it. Situation number two, I hit it and make it go back in the opposite direction. Which do you think is going to require more force? To stop it, or hit it and make it go backwards? Hit it and make it go backwards. Because here's the reason why. If you were to look at a velocity time graph, okay, let's start with that idea. If you were to look at a velocity time graph, and let's say here's 0 meters per second, if I just make it stop, my velocity time graph is going to go from some positive value to 0. If you were to look at a momentum time graph, momentum would go from some positive value to 0, right? Okay, so momentum time graphs and velocity time graphs are going to show the same shape, because if your velocity is changing, your momentum is changing. If your velocity is constant, your momentum is constant. Now, but if I take that ball and I hit it and project it back towards Patrick, what does that velocity time graph do?
Go past it.
It goes all the way through 0, right? So if I hit it, then not only am I going to slow it to 0, but what else am I going to do?
Accelerate it negatively.
Yes, now I've got to project it back in the opposite direction. So when I project that thing in that opposite direction, that's going to require more force, because not only do I have to stop it, and especially if I do it in the same amount of time. If I do it in the same amount of time as I take to stop it and project it backwards, then that line becomes much steeper. The slope of a momentum time graph gives you force. So when I project something back in the opposite direction, that's going to require more force. Now, when you look at a force time graph, you're going to have two general shapes of this. One is a nice little rectangle, and this is saying, like, basically some average amount of force acting over some period of time is going to create a change in momentum. Okay? So that's like you're driving along, you hit your brakes on your car, it's the same amount of force acting over the same period of time. Now, in reality, especially when something like it's a baseball being hit or a soccer ball being kicked, something like that, in reality, it isn't a constant force. In reality, when your foot first comes in contact and that ball gets more compressed, the amount of force actually increases to a maximum, and then when it expands back, it decreases. So sometimes you'll see a force time graph like this. Okay? And this is what we're going to call F max. Okay? But it's the same idea. So if you have a force time graph that looks like this, basically what we're saying is that over a period of time, the force is going to get bigger. So that's like when that ball is being compressed. So when Patrick threw that ball to me and it hit my hand, the force got bigger and bigger and bigger. Then it became smaller and smaller and smaller once it bounced off my hand. Now, but it's the same idea. Force max is still going to equal the area of that triangle. Now, how do you find the area of a triangle? 1/2 base times height. 1/2 force times time. So if you're looking at a change in momentum, when you get something like this, so that force max is what's going to go in there. So if it's a triangle-shaped force time graph, your change in momentum is 1/2 force max times time. Okay? So if you have a force time graph or velocity time graph that looks like this, if you have a force time graph, that F max is the peak of that triangle. It's the same idea, area is change in momentum. Now, if it's just a horizontal line on a force time graph, then it's just this, and it's just a rectangle, and it's just force times time. Okay? So if you're asked to find F max, all we're saying is that that force is not the same throughout the entire time. If it's just, unless you're told something specifically about F max, it's just force times time. Only when you are specifically told to find a force max with a triangle, that's the only time you have to worry about that. But it's the same idea, change in momentum, force times time. Now, let's look at a very, very simple situation. You got a car with a mass of, I don't know, 10 kilograms, has a velocity of 10 meters per second. No, let's make that 20. 20 meters per second. And we're going to hit the brakes and we're going to make the car stop. Okay? Do I have enough information to calculate the change in momentum of the car? Eli. Do I know the mass?
Yes. Oh.
Do I know the initial momentum of the initial velocity of the car?
Yeah.
Do I know the final velocity of
Yeah.
the car?
Yeah.
So does my momentum change?
Yeah.
Yeah.
Uh-huh.
So I could go, change in momentum is mass times V minus V9. True? Simple as it gets. So I'm going to go, oh, that's 10 kilograms times the final velocity of 0 minus 20. And I'm going to get negative 200 Newton seconds, right? That's the change in my momentum. True? Everybody cool with that? Simple calculation. If you don't like that, you could calculate the initial momentum, which is 200. What's my final momentum?
0.
0. I could take 0 minus 200. I'd still get the exact same answer. I don't care how you do it. You just figure out the method that works best for you. Now, let's say that that took 5 seconds. Okay? If it took 5 seconds, then do I have enough information to calculate the force acting on the car?
Yes.
Yes. Because change in momentum also equals what? Force times time. Now, here's the significance of that negative sign. So now I'm going to have negative 200 Newton seconds divided by 5 seconds. And that's going to get me a negative 40 newtons. Because the seconds are going to cancel out. So here's the significance of that negative sign. Okay? That negative sign is important because I've got a positive velocity, so my force has to be acting in the opposite direction to make that thing slow down. That's why I said a whole bunch of things that we've studied before are kind of going to get revisited again. Now, I want you to think very carefully before you answer this question. That took 5 seconds. Now, I want you to visualize this. We're still going to be moving at 20 meters per second. Final velocity is still going to be 0. Okay? Final velocity is still going to be 0. But we're going to take 10 seconds to do this. We're going to take twice as long. Now, listen to me very carefully. It's going to take twice as long. I'm going from 20 meters per second to 0, but I'm going to take 10 seconds. What's that going to do to my change in my momentum?
Nothing.
Absolutely nothing. Why?
Because it's still the same.
Yes, I've still got 10 kilograms times 0 minus 20. It's still going to be the exact same change in momentum because it's the exact same mass and the exact same change in velocity. But what's going to happen to my force?
It's going to decrease.
It's going to decrease. It's going to require less force. And think about this, okay? You're driving down the road. You're out here on 45th Street, okay? And you know the stoplight ahead of you, there's a lot of traffic, and you know you're going to have to stop, okay? So you're going 40. You just kind of coast to a stop, okay? Because you know you're not going anywhere, right? So your momentum is going to change, right? Situation number 2, you're driving 40 miles per hour, and a squirrel runs out, and you like squirrels, right? So you, bam, slam on the brakes. Exact same change in momentum, right? But what's going to require more force? When you hit the brakes or when you coast to a stop?
Hit the brakes.
Hit the brakes. Force times time equals change in momentum.
Change.
Okay, stop that camera for a second.
Delta P.
Okay, so on the question about the mouse and momentum, or the mouse and the elephant, don't get technical. Well, if it was a baby elephant or a really big mouse, okay? No, we're talking a normal-sized mouse and we're talking a normal-sized elephant, okay? Don't nitpick this thing, okay? Also, what up here, when I tell you, note, questions are referring, unless stated otherwise, the objects are not at rest, okay? So keep that in mind, okay? So don't get technical, well, the mouse and the elephant can have the same momentum if they're both at rest, which is 0. No, okay? Keep that in mind. When you get to question number, where's it at? On 11, okay? Draw a velocity time graph from the event. If you want to do that on a sheet of graph paper, you can, or you can just make a sketch for it. Then I say, what is the force max required and what is the average force? So what I'm asking, so visualize this on that number 11. So one on number 11, when I'm asking about that force max, visualize a graph like this. If I'm talking the average force, it's just a horizontal line like this, okay? So situation number 1, it's a triangle. Basically, I'm asking you to find the height of that triangle. So change in momentum equals 1/2 F max times time. This one, that change in momentum is just force times time. So that's going to be the difference. It's going to be the exact same change in momentum. F max, you use 1/2 F max time. The other one, you use just force times time. Okay, so keep that in mind on number 11. Okay, now we're done.
What did you say?
You're on your own.
Hey,